Hello again, everyone. Welcome back to another lecture. Today is one of my favorite topics that I like to talk about. I think it's a very, very cool lecture. And so today we're going to be talking about altitude and what happens to our pulmonary system as we go into higher altitude. And so what's going to change as far as the volume of air, what makes it more difficult, about living at altitude, and how does our body basically respond to increased elevation. And so key questions today: what effect does high altitude and hypoxia have on the pulmonary system? Remember, hypoxia is a reduction in arterial blood oxygen, which we know is not a good thing because that's going to lower our pressure gradient between the arterial oxygenated blood and our tissues who need that oxygen. We also want to know what changes are going to occur that allow humans to live at high altitudes. So probably a little bit of review, but just, addressing again that our air is made up of different gases. Most of it is actually made up of nitrogen at around 78%, and then oxygen is the second most abundant gas at 20.95, and then we have very fractional amounts of helium, carbon dioxide, and other gases that are in the air, right? But that air has a total pressure, and that's what we call the total atmospheric pressure. And here at sea level, we are at 760 mmHg. As you get into higher altitudes, that pressure starts to get reduced. But the total pressure, no matter where you are, is comprised of the individual partial pressures of the individual gases, right? So, 21% of that pressure is going to come from O2, 79% is going to come from nitrogen, and, the other small fractions from the other. But when you combine those individual partial pressures together, you get that total pressure. And so that, again, is referred to as Dalton's Law. And so here we see a chart. You've probably heard the phrase thin air before. So what does that actually mean? So, here at sea level, again, we're at 760 mmHg, and as we climb up in altitude, that air, since, we are moving away from sea level and, it's more spaced out in our atmosphere, that air gets thinner and thinner, meaning it has less pressure the higher we go. And so as you go to Denver, it drops significantly. And then you have even, places on Earth like Peru and Ethiopia where humans live at high altitudes. And so, their bodies must adapt to this because the pressure is lower. And the main reason why they have to adapt is because since oxygen takes up a relative percentage always at 21%, that means that when the total pressure gets reduced, well, then so is that partial pressure of oxygen. And so normally at sea level, the partial pressure of oxygen is around 159 or 160 if you want to round up. And then as you go to higher and higher altitudes, that partial pressure of oxygen, our starting point for that oxygen cascade, is less. And so therefore that's going to translate to less oxygen that we can utilize. So our body has to come up with ways in order to adapt and adjust. And so it's not a small percentage of people that live at high altitude. Nearly 30 million live above an altitude greater than 2,500 meters. In North America, you have the Rocky Mountains, like out in the West Coast, the Andes Mountains of South America, Himalaya Mountains, Ethiopia, like I said earlier. So a lot of people have to live at these altitudes. So because there is less oxygen available due to the lower pressures, there has to be something that allows individuals to live at these higher altitudes, because our metabolism requirements, our oxygen requirements, are going to be the same for most individuals. So because we start off with a lower partial pressure of oxygen in the atmosphere, we need to have adaptation so we could still have that same level of metabolism, whether it be at rest or during exercise. And so, as you get higher and higher, the partial pressure gets lower and lower. And so if we're talking about an extreme example, we know that a lot of people try to accomplish climbing Mount Everest, which is an altitude of nearly 30,000 feet. And the pressure, the barometric pressure at that altitude is 250 mmHg, which is significantly lower than here at sea level. And that translates to a partial pressure of O2 at 43 mmHg. That is remarkable when you think about it, the fact that people are actually able to climb Mount Everest and accomplish that goal. Because if you remember from the previous lectures, the partial pressure of O2 in our lungs, right? So even after the air has come into our body, and we'll talk more about that, in our lungs, that partial pressure of O2 is around 100. And so not even getting into the body at the peak of Mount Everest, there's 43. That's our starting point for oxygen, right? So that's going to be very difficult. And that's why, once you reach the top, you can't hang out there for too long. You take your picture and you have to come back down the mountain because there could be very serious consequences tied to that. Once you start getting to pressures above 65,000 feet, barometric pressure falls below the pressure of water vapor, which means that water vapor, that water is basically going to boil or vaporize. So not only does temperature have effects on matter, but so does pressure. And so that's an extreme example there. All right, and so, here is the relationship between altitude and pressure and PO2. So again, you see here at sea level, we're always going to be at 760 mmHg or torr, which makes our partial pressure of O2 159. And then as you climb higher and higher in altitude, both these numbers are reduced. And so how do we calculate the partial pressure of O2? And so as it gets into our bodies, like the moment it hits our mouth and our nose, what is the PO2 within that air? And so that P, the I right here, stands for inspired. So we're measuring the partial pressure of oxygen in the inspired air. So it's very simple, so in order to calculate this and find this out, you're going to take the barometric pressure and you're going to multiply by the fraction or the percentage that O2 makes up in that air. And so at sea level, like we said, the barometric pressure 760, and then you multiply that times 20.93%, which is how much, what is the percentage of oxygen that makes up the total pressure of the air. And so, for the sake of testing or, quiz questions, things like that, you could just put 21%. But that roughly calculates to a partial pressure of O2 of around 160 mmHg when we inspire that air. That's our starting point. That's how much that we have to do. And so no matter where you are on Earth, whether it be sea level, Denver, the peak of Mount Everest, in order to calculate this, how much is your starting point for partial pressure of O2 in that inspired air? Again, you take the pressure of the atmosphere and multiply it by 21. So that 21 is going to be the same no matter where you are on Earth. So if we did that for Mount Everest, barometric pressure of 250, we multiply that times 21, we get a partial pressure of O2 of around 52.5, right? So a third of what we get at sea level. And obviously, this is going to cause some complications in our body if we don't find a way to adjust. And so how do we adjust? And that's going to come through ventilation. So when we get into altitude, we are going to breathe in deeper. And so that's one of the most prominent features of acclimatization. increased alveolar ventilation with increase in altitude. We accomplish this by breathing in deeper. And so you don't think about it just as, until I say this right now, you weren't thinking about your breathing. But, when we go into altitude, those changes, that drop in oxygen, your body's going to pick up on that right away because we have what's called chemoreceptors, which level the measure of different gases and different chemicals within our blood. And so they don't acclimate to the decrease in oxygen concentration. So the moment you go into higher altitudes, you're going to have that increase in ventilation, that increase in depth. And it's going to remain there for however long you are at altitude. So it's never going to adjust. You're going to adjust, but it's never going to be turned off unless there's a complication in the nervous system. And what's going to result is what's called the hypoxic ventilator response. And just to translate that, that means because there is low oxygen, you are ventilating more in response to this. So that's the key. That's one of the major things that allows people to live at higher altitudes, that we increase the depth of our breathing, and that is going to allow for more air to get into the alveolar space, which will be used for the diffusion of oxygen. And so here we look at the cascade of air to the tissues. So we know that, within the atmosphere, again, the partial pressure of O2, roughly around, this has at 150, it's more 159, right? But so that's the O2 in the air. And then what happens is when we breathe in that air, we lose around a third of that partial pressure of O2. And we'll explain why in a little bit, but a big reason for that is because we have more carbon dioxide in our bodies and in our lungs than in the atmosphere. So this oxygen takes up a smaller fraction of that pressure, that air pressure within our lungs. So we lose a good bit of oxygen pressure due to that, and also because we humidify the air as it comes into our bodies. And so in the lungs, we get a partial pressure of O2 of around 100. And so that provides a good enough pressure gradient for oxygen to diffuse from the lungs into the blood and bind to those red blood cells. And then the red blood cells will take that oxygen and transport that oxygen to the tissues, where the partial pressure of O2 is roughly 40 mmHg. And so that provides enough of a cascade for then O2 dump off. So this is how the flow of oxygen works normally, and we covered that in previous lectures. But now what we have to introduce is, well, what's that going to mean if you are at altitude and you have a reduction in that partial pressure of oxygen when you start, right? So starting in the atmosphere, you're going to have this reduced PO2. And so now if we started at higher altitude and our PO2 was at 100, that means that it's going to result in hypoxia, because by that time that this air gets into our lungs and we lose that same fraction of O2, the partial pressure of O2 in the lungs is around 50, which is significantly less than the normal values, right? And then that's going to mean even less oxygen is going to be dumped off at the site of the tissues, which we know, very bad thing. Because we don't get oxygen, cells start to die, they can't carry out their basic metabolism, and things will go wrong. So again, how do we prevent things from going wrong? Well, we hyperventilate. And so it partially offsets the effects of hypoxia, and it will result in an increase in tidal volume. We're going to breathe in more air, and because we breathe in more air, although the PO2 of the atmosphere is not going to change, by breathing in deeper, we're going to allow more air to get into that alveolar space, the place where the oxygen and CO2 exchange actually takes place. And we're going to, reduce some of that dead space percentage, right? So more air is going to be involved in that gas exchange. And so that's going to lead to higher partial pressure of O2 in the lungs, which will translate to a little bit higher partial pressure of O2 in the blood, and more is going to be dumped off at the tissues. And so going back to why we lose some of that O2 as we breathe it in, major reason is the humidification of the air. And so when we breathe in that air, it's heated to our body temperature and saturated with water vapor. This is a good thing because, our lungs, our cells are aqueous. There's a lot of water within our bodies, and so in order to prevent damage from dry air, we humidify that air. And so it's an essential thing, so we don't create any damage within our lungs. But a consequence of it is that now, because we're adding some partial pressure now of water, that's going to take up a significant fraction now of that air coming in. And so when we reduce when we take that into consideration, that partial pressure of O2, what we get is a small drop. So we go from around 159 in the atmosphere to right when we breathe that air in and it goes past our nose and our mouth and it's humidified, we're going to reduce some of that O2 because we're adding water vapor. Again, we only have a select amount of air. If you look at it as a pie graph, each partial pressure is going to make up its own slice. And so if you start introducing, things like water vapor, it reduces the fraction for partial pressure of O2. And then it gets reduced even further. So what takes us from that 159 all the way down to 100 in the lungs for PO2 is because of CO2. So we can predict the partial pressure of O2 at the alveolar level from what is called the alveolar gas equation. So the major purpose of the alveolar gas equation is to calculate the partial pressure of oxygen in the alveoli. So we could see that in order to calculate the alveolar partial pressure of oxygen, we are going to take the partial pressure of O2 of that inspired air, and so after that inspired air gets humidified, that partial pressure is going to be around 150, and then we are going to subtract the partial pressure of CO2 within our alveoli over the gas exchange ratio. I've made it easy for you guys, as a constant of 0.8, and then we add another constant as well. But for just for your overall knowledge, know that the partial pressure of O2 in the alveoli is going to be dependent on how much oxygen we get in, and then how much CO2 there is within our lungs. And so normally that partial pressure of CO2 is around 40 in the alveoli, and then we take that gas exchange ratio of 0.8, and when we do the math, we finally get the alveolar partial pressure of O2 is 100. So we've lost a significant amount of O2 partial pressure in the lungs due to the volume of CO2. So we started off at around 160 for the partial pressure of O2 in the atmosphere, to 150 after humidification and in the airways, and then it drops all the way down to 100 once we reach the alveoli. And so how do you calculate the partial pressure of CO2 within our alveoli? Well, that's going to be through what is called the alveolar ventilation equation. And so in order to calculate that, and I'll just do this again, it's very important to know what are you trying to do with these two equations. So from the alveolar gas equation, you're trying to calculate the partial pressure of oxygen in the alveoli. In the alveolar ventilation equation, you're trying to calculate the partial pressure of CO2 in the alveoli. And that's going to be determined by the volume of CO2 that we are producing, our metabolism, how much are our cells producing as far as CO2 is concerned. And that is taken over the uppercase A. And if you remember, that's going to stand for our alveolar ventilation times a constant. So when you're calculating PaCO2, it is inversely proportional to that alveolar ventilation because we are going to likely produce the same amount of CO2 within our bodies no matter where on Earth we are. And so what happens is when you increase the depth of your breathing, yes, we get in more O2, but the reason why we get in more O2 is because we are reducing the amount of partial pressure of CO2 within our alveoli. So we'll see how this works here. If we double the alveolar ventilation, if we increase our depth of breathing, what's going to happen to our partial pressure of CO2? And so, that's basically when we go up into altitude and our nervous system and our receptors trigger that hyperventilation. That's what we're trying to do. We're trying to decrease the PCO2 and increase the oxygen, right, in our bodies. And so we'll carry all of this out here. So, consider again the alveolar gas equation. We got a partial pressure of O2 in our lungs that comes from the partial pressure of oxygen, the partial pressure of CO2 in our alveoli, and then the gas exchange ratio, which is normally 0.8 in our bodies. So, we do the math here as we did on the previous pages. We find out that normally that PaO2 is around 100, but we go up into altitude and we're going to see a severe reduction in that partial pressure of O2 within our lungs. So, let's say that, from the example from earlier, the partial pressure of O2 is reduced at altitude, and so we're going to take a starting point of 100 mmHg. So if we do the math, and that is our starting point, we're going to have a partial pressure of O2 within our lungs in our alveoli of 50, which is going to result in severe hypoxia, right? That's going to severely reduce the amount of O2 within our blood. But let's say now what's going to happen when you go to altitude is you're going to breathe in deeper. So what effects is that going to have on our partial pressure of CO2 and our partial pressure of oxygen? So if we doubled our alveolar ventilation with the same amount of metabolism, same amount of CO2 going on, what's going to happen is that because we double our alveolar ventilation, we reduce the amount of CO2 within our lungs by half, right? And so now when we plug these numbers into the equation, when we plug that new partial pressure of alveolar CO2 into this equation, well, now we go from 50 mmHg being our partial pressure of O2 to 75 mmHg, which is a lot more tolerable and a lot more maintainable as it comes to the regulation of oxygen in our bodies. So really, this main point is that when we go into altitude and we start to pick up on this increase in CO2 and this drop in O2, our bodies are going to respond by breathing in deeper. And by breathing in deeper, we increase alveolar ventilation, which is going to reduce the partial pressure of CO2 within our lungs and in our alveoli, which helps to increase the amount of oxygen, the partial pressure of oxygen within our alveoli, right? And so to what degree does this happen? Around 21,000 feet is when you typically get that doubling in alveolar ventilation. It happens at a scale, and so the higher you go, the more deeper you need to breathe in. And so here we see the effects of hyperventilation on the partial pressure of oxygen within our alveoli. So, if we have this normal ventilation here, as we start to hyperventilate and decrease the partial pressure of CO2, that's going to directly increase the pressure of O2. And if we hypoventilate or don't have that same response, the opposite effect is going to happen. So I'm going to pause the video here. We are going to talk more in part 2 about the other effects that take place when we go into altitude, because it's not just breathing deeper. There are a lot more adaptations our body has to make in order to adjust to higher altitudes. Thank you guys so much, and I'll see you in the next video.